Hello, welcome everyone. So today we have a seminar on given by to be given by Robin Kerr, and he is a PhD student at University of Gießen, and he is working on studying Anderson localization in QCD using lattice QCD techniques. So he will tell us more about his work. And so, Robin, please over to you.
Okay, yeah. Thank you very much for the introduction and also for the invitation to here. It's really exciting in India and I enjoy it very much. So I'm going to talk about the QCD Anderson transitions and I will explain what that means. I hope you can hear me well. If not, please raise the hand. And so first in the setup with overlap valence quarks on a twisted Marcy. And afterwards, I studied the influence of external magnetic fields on the QCD Anderson transition. And this work is in collaboration with Lorenz von Smekal. And the second part about the magnetic fields is also with together with Dean Valois. And it's based on these publications here. So the structure is as follows. We start with a general introduction on the Anderson transition and the motivation, why it's interesting to study it. Afterwards, I'm going to present the necessary lattice ingredients and the numerical methods I put in the appendix since it's kind of technical. So if it's time at the end, you can ask and I can show you. Then afterwards, I'm going to dive in our first setup where we did most of our studies with overlap valence quarks on a twisted Marcy. And then I'm going to talk about the magnetic fields part. And then I conclude and give an outlook at the end. So let's start with the introduction. So as probably all of you know, in QCD, we have two fundamental transitions. The one is chiral restoration and the other one is deconfinement. And so far, it is an open question whether and how both of these are related to each other. And there the QCD Anderson transition comes into play since there are relations to both phenomena. However, here we work on the relation to the chiral restoration. So what is the Anderson transition? It originates from condensed matter physics, named after the Nobel Prize winner Philip Warren Anderson. And there it describes the transition from a metal phase into an insulator phase in disordered solids. So in the metal phase, the low-lying eigenmodes of the Hamiltonian are localized and give rise to conductivity. But then as you increase the disorder and exceed the critical disorder, then all eigenmodes become localized and the conductivity vanishes.
This, of course, you are mentioning about three scale.
Three. Okay. I'm not really sure about how it is in lower dimensions, but okay. Let's assume it's 3 dimensions here. Okay. So here you see a sketch of the Anderson transition with R being some measure of localization. So R1 means perfectly delocalized and R0 means perfectly localized. So, and then the delocalized modes are separated by the localized by the so-called mobility edge. So this energy threshold here. And as you increase the volume, these curves become sharper and sharper. So in the infinite volume limit, we have a second order phase transition. And then you can also increase the disorder, and then these curves move to the left. So the mobility edge decreases and eventually vanishes at the critical disorder, and this transition from vanishing mobility edge to non-vanishing, this is also a second order phase transition. So let's go back to QCD, which is what we want to talk about it. Here we have an analogous transition. However, here we look at the eigenmodes of the Dirac operator, not of the Hamilton operator. And here the temperature takes over the role of the disorder strength. And in addition to that, you have to invert this picture. So here the low lying modes here are localized and the higher ones are delocalized. And as you could decrease the temperature below some temperature T0, which is the main quantity we are interested in our work, then all eigenmodes become delocalized. And This also intuitively makes sense since in QCD, the Polyakov loop has its ordered phase at high temperatures. And as you reduce the temperature, the amount of disorder increases. So that makes kind of sense that here now we get below T0, we get this behavior that everything is delocalized.
So all these transitions are understood in terms of the Polyakov loop, or means you are mentioning that
there is some correlation that I'm coming to that on the next slide. Yeah. So exactly this year, because it was found that the eigenmodes tend to localize in the sinks of the Polyakov loop, which means the real part, so the sinks of the real part. And then in quenched QCD, TCO actually coincides with the deconfining phase transition. Of course, in full QCD, it's more complicated, but there is some correlation to the Polyakov loop. So this is kind of the intuitive explanation for that behavior.
So when you mention the sinks of the Polyakov loop here, so the Polyakov loop sinks, these correspondences usually seen at very high temperatures.
Yes. Yeah. And that's why they have localization. And below not, because there are no sinks.
But below also there are sinks,
zero.
but those sinks may be related to something else. Because there are sinks near TC also, which are related to other phenomena like instanton ions and all.
Okay, but mainly, so the main part is everything is distributed around zero, right?
Yeah,
For the Polyakov loop. Yeah.
It is zero, but there can be deep valleys where one has negative values. Just like in the high temperature also, the average value is 1 for the Polyakov loop. But there can be deep valleys where local values were.
Okay. Yeah.
The meaning of this localized in sinks, because Polyakov loops are like Wilson loops running in the time direction.
Yeah.
So
if you take the trace and then the real part, so where the real part becomes low. So you have this, so it looks somehow like this, right? Where you have here the real part and here. Wait, is it here? I'm not sure. It's here, right? That was fine. Here the imaginary part. So and then below TC, everything is here. And then if you go above TC, then the symmetry gets broken, and then you get some more in this direction. And these are the things here.
So you define a Polyakov loop and look at things happening around that. Is that the meaning of the sinks? So
just where the real part becomes low. So these are the things. Yeah. Okay.
This is at each state. So it is integrated over time. But this is defined at each state.
But more importantly for our work is the relation to chiral symmetry restoration or breaking. So here the previous studies suggest that T0 coincides with the chiral crossover temperature. So here we're talking about non-zero pion masses. There we have a crossover. And then apart from that, it can be argued that Goldstone bosons disappear from the spectrum in the chiral limit if the near zero modes were localized. But obviously below we have pions. So this gives us a lower bound for our temperature T0, where here Tc is now the chiral phase transition in the chiral limit. So for zero pion masses, we have an exact phase transition. So we expect at latest to the mobility edge to vanish at Tc. And then also the eigenvalues are also directly connected to chiral symmetry breaking, or more precise, the near zero modes, because they produce the chiral condensate via the Banks-Kesher relation. Okay. Questions?
When you mention there is this range where you can have
Mhm.
Anderson transition temperature to be larger than the chiral symmetry breaking temperature. So what does that correspond to physically? Because I know that the chiral symmetry restoration temperature has some physical meaning. I know below
Okay.
the chiral transition temperature, the pions are the pseudo Goldstone mode. At higher temperature, it is becoming massive. And so, how do I interpret that there is another temperature with localization happening at a different temperature?
I think it's related to the correlation functions of the pion. So this is a really long paper by Matteo. Maybe we can have a look afterwards. So it's 70 pages long or so, where he argues that happens.
I would
So
think that this Anderson localization and the chiral crossover transition temperature to be coincident rather than having a different temperatures. Otherwise, it is very difficult to physically argue what is this new temperature for.
Okay, I know what you mean. Yeah. So that's why the previous study suggests that it coincides, but then we found in our work that, which we will later see, that it may not be the case.
Connection. For example, the chiral symmetry breaking is related to exciton condensation in physics, condensed matter physics. So there is a temperature at which exciton condensation takes place as a long range order. And there is a scale at which excitons are formed. So there are local excitons. So they are like preformed pairs. So that may be the T naught scale. TC is the real long range order setting. So like in cuprates also, in high temperature superconductors, you have a superconducting phase. Then there is a range of temperature, there is a preformed pair. There is not a sharp setup of preformed pair formation, but there is a crossover which looks like T naught.
Oh, means the pairs are formed at a higher temperature, but the phase locking happens later.
Exactly. So in the original one, they were all together. Now, I think with the resolution, you find that that's the, I believe, the analogy with cuprates and the exciton.
There were some studies that relating QCD phase transition with the superconducting.
Correct, yeah.
But then people have not followed it up because largely it is more difficult to establish. Yeah. But then it connects to your statement there.
Okay, so that's why interesting, because there are relations to confinement and also to chiral symmetry breaking. And this brings me now to the lattice part, where I briefly introduce the overlap operator, which we're gonna evaluate, and also introduce the ingredients we need for that study here with the magnetic fields. So in the continuum at finite temperature, so we're in Euclidean space-time, the fermion action is giving like this, where the inverse temperature is given by the time extent. And then here we have this quark bilinear, and in there we have the Dirac operator, which reads like this. And if you look at m equals 0, so this is the quark mass. If it's 0, then the Dirac operator anti-commutes with gamma 5, with our chirality operator. And as a result, then the massless action is invariant under the chiral rotations here. So this is nothing new, just a reminder. And if we then go on the lattice, so if we do a naive discretization of the fermion action via introducing a lattice spacing, then we actually end up that we describe 16 fermions, which are related to each time direction. So for each space-time direction, we get 2 fermions, and then we have 2 to the power of 4. So we have a factor of 4 for each dimension, and then we end up with 16 fermions, which are the so-called fermion doublers. And then Wilson suggested to add a term such that these doublers get removed, which effectively means making them infinitely heavy in the continuum limit. And then the Wilson Dirac operator reads like this, where we now have these group valued link variables we have on the lattice, and also here the negative direction given by the Hermitian conjugate. And however, then we have removed the doublers, but there's a problem since these red highlighted terms here explicitly break chiral symmetry, even for the massless case. So the Dirac operator, the Wilson operator, does not anti-commute with gamma 5 anymore, which is a problem. So then you could naively thinking about adding another term, so you restore the chiral symmetry, but there's this Nielsen-Ninomiya theorem that it's not possible to maintain chiral symmetry and a doubler-free lattice formulation, at least not in an exact continuum sense. But then there's the solution to that, which is the Ginzburg-Wilson equation. So if you rephrase it in this form, then it reads like the continuum criterion for chiral symmetry. However, you have to modify this gamma matrix by this red highlighted term here. And since it goes with A, then it vanishes fast in the continuum limit. Okay, and then let's talk about some properties of the eigenvalues and eigenvectors of the Dirac operator, which are our main interest here. We want to compute them. So if D is gamma 5 Hermitian, which usually most Dirac operators are, then the eigenvalues come in either real or in complex conjugated pairs. And then if you additionally require that the Dirac operator fulfills the Ginzburg-Wilson equation, then we can derive that the eigenvalues lie on a circle in the complex plane with a radius 1 over A. And also additionally, if V lambda is an eigenmode of the Dirac operator, then it follows that the eigenmode of the complex conjugated eigenvalue is just gamma 5 times V lambda. So they're directly related to each other. And then obviously if you go to a smaller lattice spacing, then the circle increases more and more. So at the end, we end up on the imaginary axis where it should be in the continuum limit. Okay, and then one solution of the Ginzburg-Wilson equation are the so-called overlap fermions, where the overlap operator reads like this. I will explain in a second why here A tilde appears. So we have, apart from that, 1 plus the sine function of some kernel operator K, which is mostly the Wilson operator. And it is required that it's gamma 5 Hermitian because that ensures that this sine function is well defined via this relation. So we have an inverse square root here. Okay, so as I already said, usually we use the Wilson operator, which we also did in our work with a negative mass shift rho. I explained in the second what this does. And then now I explain why we have A tilde here, which is just A divided by rho. You need this factor to obtain the correct continuum limit. And then, of course, in the continuum, the Dirac operator is strictly local. But due to the inverse square root, this is not the case here. But however, one can still show that there's an exponential decay, and so you still have locality. And this locality you can optimize with this parameter rho between 0 and 2. Okay, so far so good. Then we come, so far the explanation was for our first setup. So this is for the second setup now. where we employ staggered fermions, however, in a magnetic field. And that means we have to insert these U1 link variables here to implement the magnetic field. And okay, apart from that, we have these staggered phases. So we transformed the way the Dirac structure and simplifying everything, so they're really cheap. So that's also why we chose them for first study. And okay, then there's another thing we have to think about, because we are on a torus, we have periodic boundary conditions. That means if you think about a particle traveling around a closed trajectory, then the magnetic flux is ambiguous, because you can either choose this area here or everything else than this, so the other part. But still, the phase the particle picks up has to be the same. So we have this condition here, and from this we can derive a quantization condition for magnetic fields, which we have on a torus. And here we put in the down quark mass, since it's the small fraction of the elementary charge that exists. So it also works for all quarks. So NB is here the magnetic flux quantum number. So with that, if there are no questions so far, I go to our first setup now with overlap valence quarks on a twisted mass C. So here we compute the low-lying eigenmodes of the overlap operator with the Wilson kernel I just presented, and the gauge configurations we take from the twisted mass at finite temperature collaboration, which, as the name says, are generated with twisted mass Wilson fermions and the Iwasaki gauge action. And here we have two degenerate, still non-physical light quarks, but physical strange and charm quarks. So we have this is a so-called mixed action setup, since we employ other fermions in the valence band than in the C. And this kind of mixed action setup is actually well studied. So usually you have to do some matching, because they converge differently to the continuum limit. And here was studied that if you adopt the lattice spacing from these twisted mass configurations and then match the quark mass, then you actually get a well-defined continuum limit and extract f pi, mn, and m delta. So in principle, this approach works, and that also justifies why we adopt this lattice spacing here, just for here. And also it was studied how can we optimize the locality, and here rho equals 1.4 seems to be a good choice in a slightly different setup with just two flavors, but it's enough to justify to take it. So here you see an overview of all the configurations. So we have a large temperature range for 3 different setups. Here we have the largest lattice spacing, 0.09, and for the others we have 0.06. And then also there are different pion masses. So for both of these, the pion mass is roughly 370 MeV. That's why they're called like this, A 370. So the letter refers to the spacing. And here we have D 370. And for the most physical setup, we have a pion mass of 225 MeV. Why is it still called 210 MeV? It's because in the past, the pion mass was determined to be 210 MeV, and it got improved now. So it's a little larger now, as well as the pseudocritical temperature, which is around 170 MeV. And that for this setup, so we put the main focus on this, since it's the most physical one. And here two very interesting temperatures according to my introduction. So for NT equals 18, we are very close to TPC, and for NT equals 24, we are really close to TC. And we expect the mobility edge to vanish somewhere there. Yeah.
The chiral transition in the massless limit.
Yes, exactly.
And how is it extracted?
This is from the hot QCD collaboration.
Yeah.
So
but
independent calculation, not in these setups.
Okay. Yeah, but these setups are very different.
Yeah.
Because
yeah.
hot QCD uses different fermions.
Okay, but that in the chiral limit, that's the value.
In the continuum
so
limit, of course.
It's an independent calculation. I think with highly improved staggered fermions. Yeah, it's based on yeah. I think I understood already. It's based on zero temperature calculations. So there's another collaboration, the European Twisted Mass collaboration, and they do the zero temperature calculations, and then the Twisted Mass at finer temperature collaboration takes this as a starting point.
You just use the kappa that you have used in the pure temperature configuration
Yeah, exactly.
To generate this. Okay.
Yeah. It gets generated based on these. So this lattice spacing here is from the zero temperature calculations. Yeah. Yeah, this refers to the chiral limit. Yeah. This was I think it's his, yeah.
This has also been verified using the different formulation like domain wall or Wilson, twisted Wilson. Or
I know about two papers. They computed that and they agree. So the other one is basically on these twisted mass ensembles, but with a physical pion mass, which we could not evaluate yet because it's too expensive.
Okay.
Yeah. So that has been verified there too. But of course, this value is independent of these ensembles here, because here we can just extract the pseudocritical temperature based on these ensembles. This is independent of that. But we expect at latest the mobility edge to vanish there. That's why we look at it. Okay. That's maybe a little bit technical. Then we also do a stereographic projection. So usually we are on the Ginzburg-Wilson circle, but then we project onto the imaginary axis where the eigenvalues should be in the continuum limit in order to hopefully improve the limit a little bit. And so therefore we have to require, maybe I showed the picture already. So of course, if Z is really close here, then it just has to map on itself. So we have this condition here. And when we are on this side of the circle, it has to get projected to infinity in order to make sense. And this then singles out the so-called Möbius transformation, which can be translated to the stereographic projection, which you see here. So we go through this point and through the eigenvalue on the Ginzburg-Wilson circle and project it on the imaginary axis. And here you see an example how that looks for one temperature. Okay, that's not too complicated. So now we come to some results. So at first, since I mentioned the Banks-Kesher relation, which gives us a condensate by the near zero mode density. So here we are looking at our coarsest and heavy pion lattice first. So below TPC, which is around 185 MeV, we see a near zero mode density, which builds the condensate. So this makes sense. So these are all the temperatures below. And then if we go above, then we still see a near zero mode density, but it starts to decaying and eventually vanishes at high temperatures. And this makes sense because we have crossover and no sharp phase transition. So we don't expect it to disappear immediately after the crossover.
But even if there are these small pockets, that doesn't mean that psi bar psi is finite. You can have like,
I mean,
yeah,
if you renormalize.
yeah.
Okay. Yeah. There's also this.
The psi bar psi goes to 0 after this temperature. Renormalized one.
Okay. So probably it goes if you make the renormalization, it probably goes way faster, but you also don't expect it to disappear immediately, right?
There will be some mass effects, but small effects, m square effects, light quark mass effects. But
okay, yeah. Thank you for that comment. So okay, but yeah.
So just my ignorance, essentially. So I mean, what is the analog of this quantity in the usual Anderson localization transition in the condensed matter context?
I don't know of any analog concerning the distribution. Since the Anderson transition is about localization properties, and we're not talking about that yet. I will come to that later, but I'm not aware of an analog. Maybe there is one, but I don't know one.
you mean an order parameter? You mean? Because that is a more geometric phase transition. So yeah, I think something related to like the fractal dimensions or IPR or IPR kind of inverse. Okay.
So we are coming to IPRs later. But this is just a
quantity. So that happens, what connection we should have to the condensed matter context? Because I'm ignorant to profession.
Oh, this psi bar psi.
Yeah.
So just I wanted to, you remember, you talked about twist and the change in parameter with the twisted boundary condition. So that is used in the scaling theory of Anderson localization to calculate beta function. So do you attempt to do that also?
Sorry, I'm not sure.
There is something called scaling theory of Anderson localization.
Yeah.
Whereby you look at the extended region of extended space and twist the boundary condition. So that change leads to some energy shift. So that is like conductance change. So there is a beta function in the evolution equation of that. Okay, there is no.
This one is a little bit different. This is for gauge configuration generation difficulties.
Yeah.
But on the measurement level, there is no
twist.
Yeah.
Like geometric density of state.
So we have just ordinary boundary conditions, periodic in space and anti-periodic in time.
That's what the
Yeah.
twisted boundary condition. You say that it's wave function pi and plus and minus 1 and plus plus. So see the energy difference. That becomes a measure of beta function. You can chat.
Okay.
I'll just ask one question. So given the current setup that we have used, where your light quark was tuned to 364, you get the crossover around 185 with error.
Yeah.
So maybe if you could have configurations which tune to maybe lesser 250 MeV, do you expect the crossover temperature to go down?
Yeah, it goes down. Yeah.
So
basically that's what you see in the. Oh wait, what's the table? In the table. So so I just showed these pictures here to A 370, where we have 185, and then if we go to D 210, then the pion mass gets from around 370 to 225 MeV, and also the pseudocritical temperature reduces.
Okay.
And I should also mention, so probably this TPC should be higher here. So in the past, the determination was, so it got improved. So in the past, also this pseudocritical temperature was at 158 MeV, which would be almost physical. So it's not, it's not really believable, but it got increased. So this probably also maybe 195 MeV. It should be higher a little. But yeah,
Okay.
so as you reduce the pion mass, the pseudocritical temperature also reduces. Was that
Okay.
your question?
Yeah, I think that was my question. You already, I think,
Okay.
answered.
Okay.
I have another small question, if I may. So, if I understand correctly, these are Clover fermions, right? At the gauge configuration generation
No,
level.
this is twisted mass Wilson fermions.
I see. So you add a twisted mass in the action to avoid zero spectrum in your eigenvalue of the D inverse.
So can you repeat?
My question is whether if you are adding a twisted mass in your actions while generating gauge configurations, you have to reweight it any observable if you are calculating.
Because I'm not really familiar with these ensembles. We take that from another
Okay. Then,
collaboration.
yeah, it's okay.
So we take these as input for the overlap operator. So the spectrum we compute on the overlap operator.
I see. Okay.
So now we get to the localization part. So first we have to talk about how do we define this. And here we employ the inverse participation ratios, which are given by this formula here. And Q is the order. So here we take the second order. And then if we take the inverse of this and divide it by the number of all lattice sites, then we get a quantity between 0 and 1. And then 1 would mean perfectly delocalized and 0 perfectly localized. One could in principle also take higher orders, but then the corresponding relative volume which you define would get more and more suppressed. So here you see the most. And also border on 1 doesn't make sense because then everything is just 1 and we don't see anything. So, okay, I just explained this part. It's easy to check. Then if it's localized, then it approaches 0. And if it's maximally delocalized, it approaches 1. And here you see an example where we also compared the rho parameter. So we set it to 1.4. And comparing it with 1, you also see that it works much better. So here we get way more localized modes, or here basically no mode is really localized, so we don't really get to the 0. So it seems to be a good choice. And yeah, then you clearly see here some transitions. The low-lying modes are localized and the higher ones delocalized. So then we need some criterion to quantify the transition, and it's natural to employ the inflection point. Yeah.
What is this parameter?
It's the parameter you use in order to optimize the locality of the operator. So there is an exponential decay, and with this parameter you can optimize this. Yeah. And this also apparently reflects in the localization of these eigenmodes. Okay, let me briefly explain how we extract the inflection point. So here we get some scattering. So it's natural to perform a binning. So basically we compute the expectation value of R of lambda such that we obtain data with standard errors as usual in Lattice. And then we vary the bin size and fit window in order to get good fits with a chi-square as close as possible to 1. And as fit ansatz, we use a Taylor polynomial around the inflection point. So the second order vanishes, and then we can just read off the inflection point, which is denoted by lambda c here at the end. And this procedure works very well, since here we are really up to 2 digits, we reach chi-squares of 1. These red vertical lines indicate the fit window here. And in the table, it's also denoted, and also the bin size. And so this is the result, what we get for one example temperature, our mobility edge.
And this
Yeah.
fit window, how stable is it? Like to increase to higher order polynomial, Is this fit window stable?
Yeah, this is kind of stable. Yeah. But I will mention that in the outlook we also want to improve that, since this is just one fit, and we plan to really make a model averaging, try different fit windows, different bin size, different fit ansatzes, and then average over all of them. Since sometimes it really can change a little bit. So if you choose the fit window,
Kept the quadratic term to be 0, or it came out from a fit?
yeah, it is 0 by definition because we have a Taylor polynomial at the inflection point, so this vanishes. So this is our ansatz.
That is fine, but
Yeah.
I think the data may not be so sharp. Detect the inflection points. That's fine.
Yeah, okay. Okay, maybe one can think about it.
If you include this,
But-
this order versus you exclude that, then how much is the chi-square changing?
Yeah.
What is the coefficient of?
You mean in comparison? Yeah. Okay, that makes sense maybe. Yeah. Because otherwise, if we have it in there and then we get a coefficient which is non-zero, that means we are not at the inflection point, right?
Zero.
That
It is fine.
it should be near zero. But yeah, so I agree. One could implement it afterwards and see what happens if it's stable. That's true. Yeah. No questions so far? So then we come to the results for the relative volume. Now we are at the coarse heavy pion lattice again, where we have this transition temperature of 185 MeV, and below we see there's no inflection point. We have no mobility edge. But here we all have all the higher temperatures where we everywhere find a mobility edge. So this is consistent with earlier work, which I showed in the beginning, that the mobility edge vanishes around the pseudocritical temperature. So let's go on. And also, if we try to extrapolate it, here we have a... Yeah.
It's like, so the bins are changing very fit windows.
Yeah, it's changing a little bit. We tune it. Yeah.
So this you already you fine tune it for every temperature,
Yes. Yeah.
and your statistics is almost same for every temperature. It is varying a bit.
So here we have for these, except for one, I think except for this here, we have evaluated 200 configurations. For this
Okay.
one, 150. For this one, also 200. And for these both, these have a larger lattice size, because you need to keep the aspect ratio probably. There we just have 50 configurations, but then the density increases, so it's also good statistics.
So the statement is that if you go to higher temperatures, you don't have this intercept in the eigenvalue density, and then the mobility edge actually is deep inside the bulk spectrum.
Yeah. Okay, here I'm not sure actually, because here it's really close to 0. So if
But that is also very close to your transition temperature TPC, right?
yeah. But
all
so
other
your question was
temperatures,
about that infrared part?
yeah,
Yes.
these are not belonging to the infrared part, this small peak of eigenvalues. So
Yeah, so here maybe we are already a little bit or very close to the infrared part. If you look at
can you show you? Yeah,
if you
that will
look at
help.
the distributions. So here,
So the infrared part is like within 200 in MeV units, right? Yeah.
yeah, it's 190.
Yeah, but the lambda is around within 200. So lambda by T should be 1.
Oh, wait, where are we? So around 200.
Yeah.
And here it's also,
Yeah, so the mobility is far away
Oh,
from
it's-
200.
it's 120 or so. So it's
But for the other
at
ones,
least-
it is far away from 200. Only for
yeah,
that.
then it's far away after
Yeah.
that. For that temperature, it's
This temperature, I'm a little bit
enters.
worried. This result may not be a little bit, because it's not following the trend from the other higher temperatures. In the other higher temperatures, your mobility edge is much far off from the small pocket
Yeah.
of modes. Only
Yeah.
only at one temperature you are seeing this. So
Yeah, so we have to be careful because of the infrared spectrum. So that was a study from the past. And then later we
No.
realized this problem with the infrared spectrum.
No,
which I
we
will
understood
explain
that
later.
because there can be remnants of phase transition in this region.
Yeah.
So it is very difficult to remove
that as well, yeah.
remove the Anderson effects
Yeah.
and this localization effects.
Yeah.
Because this is not like a normal Anderson model where there's only geometric phase transition. There is also real phase transition happening. So the small modes have this information of the phase transition just near the more complex.
Yeah, so one has to be careful when it's really close to TPC. Okay, and then when modeling the temperature dependence, so here we have a quadratic one, even though this is well described by a linear fit. So if we fit it, this coefficient for the quadratic term is consistent with 0. This is also in agreement with the past where linear dependence was observed. And yeah, as you just mentioned, Sayantan, here there seems some kind of drop happening since the extrapolation lead here already leads a little bit below TPC, but we just saw that that's already vanishing. So here's some drop which has to do with these difficulties you just mentioned. And okay, why do we have a quadratic term here? It's because then going to the D370 lattice, where we now have a smaller lattice spacing and also a larger, the volume is roughly the same, I guess, a little larger maybe. No, it's roughly the same. And the pion mass is the same, basically, 370 MeV. And here, you might see it a little bit, here we get a slight curvature. And here the extrapolation yields a 0 below T, the pseudocritical temperature. And then we also have higher volumes here, which are not included in the fit because you have to justify somehow. You have to compare equal volumes with equal volumes. And here it becomes higher, but they indicate, as they're obviously then more physical, that the mobility edge indeed does not vanish at TPC as was observed earlier. So here a change comes in. So it doesn't look like there's vanishing at TPC anymore, which is due to this curvature coming in here. And also in this paper from the past, you actually see a slight curvature as well, but really slight. You have to basically put a ruler at the screen to really see it. But they said that it's well described by linear behavior. So these are already first indications for that. And now we go to closest to physical lattice, where we're now at 225 MeV pion mass. And also what is important, the volume is larger than for the other ones. So here we have the chiral phase transition temperature and the chiral limit, which we were just talking about from an independent calculation. And here the pseudocritical and the temperatures in between. And here all the higher temperatures, and everywhere we find the mobility edge. So this looks kind of surprising since we expected it to vanish it in that interval somewhere, but it does not.
Again, here one has to be careful about the phase transition effects.
Yeah. The phase transition and also
because as soon as you go to higher temperatures, your eigenvalues, the critical eigenvalue, the mobility edge goes to very large values, which has nothing to do with this small localized modes of the eigenspectrum. Like for example, if you have 266 MeV,
yeah,
there your mobility edge is around 500 MeV, which is deep inside the bulk modes.
Yeah. Yeah.
Only for
Yeah.
the small temperature range, you have this mobility edge,
Yeah.
which is closer to
Yeah,
small
because
mode.
there we have this infrared part, which I
Yeah,
wanted.
that I claim that it is, as Ravi's work was there, it's
Yeah.
more related to phase transitions. So
Yeah.
one has to be careful about that.
Yeah, exactly. So now the question, okay, I'm coming to the explanation in the second slide. If we include these points below TPC, if we exclude them from the fit, then actually we find that the scaling fit works well, better than the quadratic one we used before. So this somehow indicates the nature of a second order phase transition. And also the QCD Anderson transition is expected to be in the universality class of the unitary Anderson model. And if we consider that we included all the temperatures in the fit, then this is still in reasonable agreement, since we cannot expect the scaling window to be that large. So, but we don't have enough points here to really shrink it. But we have tested it. If we go maybe exclude the highest point or include next to leading order scaling corrections, then actually this coefficient tends to increase. So
if
maybe
you remove the points near 200 MeV, what will happen?
so these
Yeah, just near TPC, sorry, the pseudo-critical temperature.
I'm not sure I have to try, but it looks like it's going a little bit upwards again. Yeah.
So you removed all these points between these two vertical lines.
So the red ones are excluded. So you want to exclude these
Even these two, yeah.
these two as well.
Yeah.
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 One could try that. Yeah. I think, yeah. Maybe it's back to TPC then. Yeah. Yeah.
Because your higher points are having larger curvature, and these points may bring it down. So your
Yeah.
exponent may be coming to 1.24 because of these lower points, few of them.
Yeah. Yeah. I think, yeah, it's interesting to try. But then, yeah, the key question is still, why does these data points deviate from the fit, which we also saw an indication in the coarse lattice already, as we just discussed. And for that, I have a possible scenario, since we look at the relative volume. So even if it would be small, it could still be the case if you increase the volume that it scales with the volume, that it increases according to some effective dimension d. And if this is non-zero, then it means that they are not truly localized. So this is a problem which we cannot see with the relative volume. For this, it still looks localized, but in order to study this, one really has to compare several volumes with each other. But we have huge computational costs, so at the moment we cannot afford that. But it was done in quenched QCD, at least. There they did this. And there they find a second mobility edge at lambda equals 0. That means the exact zero modes are then delocalized because they have this scaling with the volume. And then we have this band of localized modes, and then the other mobility edge comes in, and we get to the delocalized regime again.
Yeah, one problem I have with this picture is that this is in quenched QCD. It's not dynamical.
Yeah.
So it doesn't have any chiral symmetry breaking built in it.
Yes, that's true. But
So-
so Ivan told me at the Lattice there's a paper about full QCD now, and it basically agrees so far.
Yeah, but still, I have some.
Yeah, still, yeah, it's not super clear,
Yeah.
of course, yeah. Okay, and then if we look at our distributions, so the vertical red lines is the mobility edge lambda c we extracted from the inflection point, which decreases together with the bulk spectrum as we reduce the temperature. But then you also see this infrared part. So here you see an infrared peak. And as you decrease the temperature, this becomes broader and broader. So it's reasonable that if there's such a second mobility edge at lambda equals 0, that this moves upwards as the spectrum becomes broader. And then it could be that both mobility edges annihilate each other. So, yeah, which we just discussed a lot. We have to be really cautious when these both spectra hits, then the method doesn't seem, and also the observable doesn't seem to be reliable anymore. When the spectra merges, which occurs at roughly TPC maybe here, but it also could be higher. So this infrared phase occurs above a temperature of 200 to 250 MeV, but in quench QCD. So in full QCD, it's not clear so far. But there might be another observable investigated by these gentlemen here in the front, where we employ the level spacing statistics. So the level spacing is the difference of two consecutive eigenvalues. And then when we look at ratios of these and take the minimum of both, then we also have a quantity between 0 and 1. And it is known from other studies that the delocalized modes, so the localized and delocalized modes follow different statistics. It's the chiral Gaussian unitary ensemble for the delocalized ones.
Sorry.
So,
No, it's
okay. Okay.
Yes.
Okay. So it's this one for the delocalized ones, and there for the expectation value of R tilde 0.6 roughly is predicted. And the localized modes follow Poisson statistics, and there it's predicted to be at roughly 0.39. And then indeed, so here we have the lowest temperature of our most physical observable. So here we're really close to the chiral phase transition temperature. Here we indeed see just delocalized modes according to this observable. But in principle, we see this quantity does what it should. For much higher temperature, we see here these localized modes. However, with bad statistics, since the localized modes are really rare, so we really have to increase it to really make a statement about that. So ideally, we could also try some mobility edge estimation according to this observable, but yeah, right now it's fluctuating too strongly, and we have to increase the statistics, evaluate more configurations. Okay, let's go. So that was everything to the first part. Now we come to the second part, where we study the influence of magnetic fields on the QCD Anderson transition. So we're mainly interested in the transition temperature. And what is the motivation behind it? It's known that magnetic fields reduce the chiral and the deconfinement transition temperature. And if we expect that, or if we assume that the QCD Anderson transition is strongly related, then we would expect a similar behavior for that. So that's the main motivation. And for the magnetic, for the chiral transition, the mechanism is as follows. Namely, magnetic fields enhances the chiral condensate when we're away from TPC, but then close to TPC, it gets suppressed. And then as a result, the transition temperature goes down. And for the deconfinement, Okay, we have to be careful. When we look at the Polyakov loop, it's obviously just an order parameter in the quench limit. There we see that the magnetic field enhances the Polyakov loop everywhere.
In the case of Lennard's metal, apply external magnetic field, then it has drastic effect. Like the time reverse paths do not interfere. So there is absence of localization in the Anderson localization of electron problem.
From magnetic fields?
Yeah.
Oh.
Suppose I start with a localized state, apply a small electric field, small magnetic field, then coherent backscattering is suppressed because of external flux.
Okay.
So there is some dramatic change. I wonder if there is anything similar to that with your color magnetic field here.
So what changes? Is everything, what happens? What exactly?
So the nature of
U1
magnetic field. So then similar things
quarks are covered. And also quarks
carry electric charge.
They're competing stuff.
Okay, we can chat.
Okay. All right. Okay, so far to the motivation why it's interesting to study that. And here is a brief explanation of our setup. Here we now use the staggered operator. So we compute the eigenmodes of the staggered operator, the low-lying ones. And now we also have staggered fermions as input. So here we have a uniform setup, not mixed action as before. And as well the semantic gauge action. The lattice is here really small. Here, however, everything is fixed. So the number of space sites is 24 and the number of time sites is 6. So here we vary the temperature via the inverse gauge coupling. The other setup was fixed scale. This is not fixed scale now. Here it's varied via beta. And then as I presented earlier, the magnetic field is then quantized because we are on a torus according to this condition, where NB is our magnetic flux quantum number controlling the magnetic field strength. Then I come to the results. Here we have a high temperature. We had around 400 MeV. And here we see as we increase NB, the mobility edge gets reduced. So it decreases. The increasing magnetic field reduces the mobility edge. So if that would happen everywhere, then the transition temperature would actually be higher at the end. But if we go to lower temperatures at 200 MeV, then the mobility edge seems to coincide for all magnetic field strengths. So this happens roughly about when the Banks-Kesher gap closes. And if we go to even lower temperatures, then we have this turnaround behavior. So now the magnetic field increases the mobility edge now. And if you would further reduce the temperature, then these inflection points for the low magnetic fields would vanish at first, since everything moves to the left, but there's still a mobility edge for the high magnetic fields. And that as a result, we have a reduced Anderson transition temperature, which we called T0. So in this first setup with staggered fermions and also the small lattice, we observe exactly what we expected. But obviously, we have to go to higher lattices to really confirm that and see what happens there. Yeah, you built in these U1 links in the action.
I made a statement about this magnetic field. So I made a wrong statement because it's true only in 2 dimensions. Because in 2 dimensions, according to theory, all states are localized. Even small disorder. But however, if you apply magnetic field, because of this buried phase coming from magnetic flux, the theorem is no more true. It's called anti-localization. Specific to 2 dimensions.
Ah, okay.
Not to 3 dimension that you are discussing.
Oh, okay.
Maybe there is something similar to that here.
But
Okay.
if one goes to very strong magnetic fields,
Very strong, then
we go to effective
2 dimension. Yeah. There it's for arbitrarily small field, it will anti-localization.
That is what they're seeing, right? High temperature. I don't know how much is a magnetic field in the physical units.
I have to compute. Yeah, since
Magnetic,
So it's effective.
probability it is reducing.
And it's like anti-localization.
But it is very different from the Lattice.
Correct.
okay. So this brings me to the conclusion and outlook. So the conjecture on the QCD Anderson transition is that for non-zero pion masses, this annihilation of both mobility edges is a very possible scenario, at least for the twisted mass ensembles where we have these infrared peaks where we observe them. And we think that we at 0 pion masses, or if we somehow subtract the infrared spectrum, that then we might have a second order phase transition at TC, at the chiral phase transition temperature. And regarding the magnetic fields, the magnetic field really seems to decrease the transition temperature. And since there's also this turnaround behavior, as you also see for the inverse magnetic catalysis, it's reasonable to ask the question whether there might be some relation, and we want to figure out. And as an outlook, it is planned to study domain wall configurations together with Ravi and Sayantan. This is interesting because we then also have chiral fermions in the sea. And also there we don't have this infrared part yet, and but physical pion masses already with lower lattices. And then it's still planned to evaluate these twisted mass ensembles for the physical pion masses, which however are really, really expensive. So we have to reduce computational costs, and there are many ideas how to do so. One is UV smoothing, one is constructing a multi-grid method, since we have to solve a system of equations, and this is best suited nowadays for this, and used very widely in lattice studies already. And then it would be interesting to try to identify the mobility edge, or maybe both mobility edges if they exist. But for that we have to increase really the statistics, because these low-lying modes are really rare. And as I already mentioned, for magnetic fields, we want to analyze larger and also finer volumes. And also, it's interesting to somehow try to model the B dependence, how the mobility edge depends on the magnetic field. And yeah, for a lot of points, we also talked about that. It's also important to improve the determination of the mobility edge by doing such a model, averaging, choosing different fit ansatzes, different bin sizes, and yeah, also different fit windows. Then I have an extra slide, since I did a lot of fitting in the work. So here you see the official marathon world records on the y-axis. And then I tried to model it somehow when the magical 2-hour mark will be broken. It has happened already in an unofficial, artificial setup, but so far not in an official marathon. So I tried to model this, and here the data is well described by a linear fit. And so my prediction is that it will be done in 2028 plus minus 1 year. So let's see whether that applies.
Have you taken it up on machine learning.
No, that's just a fit. So I just took the data from Wikipedia and just a linear fit. It works well here. Yeah, and with that, thank you very much for your attention.
Thank you very much, Robin, for this exciting talk. And